The title of this video is Periodic Table of Elements, and I picked this particular subject to talk about because it seems to me that understanding the periodic table of elements is really a key step in doing well in the Regents, because so much information is you can deduce the necessary pieces of information that you need to answer your questions really right from this table. A lot of the information is just here, you just need to know how to interpret it. So quickly, to describe or explain how the periodic table is structured, it's divided into periods and groups. The groups are numbered 1 through 18, and each of these groups exhibit a certain characteristics. For example, Group 1 is labeled or called the alkali metals. Group 2 is labeled alkali earth metals. Group 17, halogens. Group 18, noble gases. Excuse me. And each of these groups, elements in these groups exhibit similar characteristics. Except for hydrogen, which is an exception, it doesn't exhibit the same characteristics as these metals over here. Periods are labeled 1 through 7, and they don't have the same sharing of characteristics. Rather, there are certain trends that follow moving from left to right on the periods. Talk about basically the composition of these elements. You have metals and nonmetals. To the left, you have the metals. These are the most potent elements. They're going to want to react very readily. And some metallic qualities include luster, conductivity, which is conducting electricity, ductility, which is the ability to make wire out of metals, and malleability, the ability to work with these metals. Groups 3 through 12 are transition metals. They will be moving more towards nonmetals and losing those metallic characteristics. The elements that are bordering this zigzag line, they are metalloids, and many of them exhibit characteristics of both metals and nonmetals. Finally, the elements over here, nitrogen, oxygen, fluorine, for example, they are all nonmetals, and they exhibit characteristics such as being brittle, lacking luster of the metallic elements, and poor conductors of electricity. So that's the basic composition of elements. There are a couple of things that I'd want to talk about inside the periodic table. And a couple of these things include atomic radius, electronegativity, size, and ionic radius, and ionization energy. But one of the biggest ones is atomic radius. And so, if I briefly explain how atomic radius works, I'll put the periodic table here so it's easily you can reference while I speak. When you move along a period from left to right, you are adding electrons to a shell. And so if this is the first shell right here, and this is the second shell, and for example lithium will have a configuration of 2-1, just make sure this is caught into the, it's caught into the camera, 2-1, it's going to be adding, as you move from lithium to neon, you're going to be adding electrons successively into this shell. Inside here, electrons, as you know, are negative, and inside the nucleus there are protons, and these are positive. And so these protons are going to pull on the electrons, and it doesn't matter how many electrons are actually in this shell. Speaking of atomic radius, the more protons you put, or when you're moving from lithium to neon, you're adding protons into the nucleus. You're going to create a bigger nucleus with a greater positive charge, and it's going to pull more on those electrons. So the same configuration now to 7 of fluorine is going to have a tighter atomic radius. Now, atomic radius, by definition, is the measurement between one nucleus of one element and another nucleus. I drew that a little too spread out, but the distance between the two halved, because you can't actually measure the distance from one nucleus to the outermost electrons. But if you have it between two, then it's a precise indicator of the atomic radius. So it's the measurement between the proton, from the proton to the outermost electrons. So the distance between the nucleus and the outermost electron of lithium is a certain amount, and the distance between the nucleus and the electrons of fluorine is a much smaller amount. And the reason being is that, again, the protons pull on those electrons. So for those of you who like to memorize, the trend for atomic radius is as you move from the left side of the periodic table, you're going to decrease in atomic radius. And it's the same thing as you go on. There is one catch though. As you move from each of these successive periods downwards, you're actually going to experience a big jump. And the reason being is because you're going to add an extra as you move from neon, which has a configuration of 2, 8, to sodium, which has a configuration of 2, 8, 1. You're adding a whole new orbital of electrons. And even if there's one, it's going to be orbiting at a certain speed and occupying that space. So the atomic radius is going to increase by a huge amount when you move from one period down, one end of the period on the right side to the next element successively. And I forgot to mention this, but the periodic table is organized by atomic number. So that atomic number represents the amount of protons. And here in this little chart here, hopefully you can see, it labels what the numbers mean. So the atomic number, for example, for carbon is 6. It has a configuration of 2, 4, which means it has 2 electrons in the first shell, 4 electrons in the second shell, and since it only has 6, you have to have the same amount of protons as electrons in an atom. Not the case in an ion, but in an atom. You have 6 and 6, and a certain amount of neutrons, depending on the atomic mass. In this case, there are also 6 neutrons, and the way you get that quickly is you subtract the atomic mass from the atomic number. Because if the electrons and protons are the same amount, and electrons don't weigh anything because they don't have much mass, or nearly any mass or practical matter, the rest of the remaining mass is just neutrons. So between 12 and 6, there are 6 protons in carbon and also 6 neutrons in an atom. There are also different isotopes of carbon, carbon-14, for example, which is used in dating, and that has atomic mass of 14, which means it has 8 neutrons instead of 6. So that's just quickly to explain to you what these numbers mean if you didn't understand that already. The next subject I'd like to talk about is electronegativity quickly. I'll write that down on the piece of paper. And electronegativity is an attraction of an element towards electrons. Now, you probably know by now that fluorine has the highest electronegativity of 4.0. You don't really have to know this because it's all given to you on your Regents table, but it's good to kind of understand how it works. So this is one of the trends that you do need to know for the Regents. The general trend for electronegativity is from the bottom left corner of the periodic table, starting from francium, all the way to fluorine, which has an electronegativity of 4. And so the logical explanation for this is that fluorine has the atom has 7 electrons, and it would like to really gain 1 electron to be stable because it's most stable in the 2-8 configuration when all the electrons are levels are filled. While an element all the way on the left, lithium, or for that matter any of these elements, lithium to francium, they have 1 electron in their outermost shell, and they would like to lose that electron so that they would too become stable. So therefore, when I have a positive charge on the left side, those elements are going to want to give up that 1 electron, and therefore they're going to have a low affinity or a low attraction for electrons. And part 2 will continue.